So the last talk of this session is given by Viktor Palmkvist. The title is Statically Resolvable Ambiguity. Just wait a few seconds and we can start.
Hi. Hi, I'm Viktor. I'm here from KTH in Stockholm to talk to you about syntactic ambiguity in programming languages. Now, let's start with the elephant in the room, which is what's syntactic ambiguity? Programming languages do not tend to have syntactic ambiguity by design. They're constructed to never have it. In fact, I'd guess that a fairly large portion of the audience in this room have either given or taken a course on parsing that have gone something like this. This is an intuitive grammar for arithmetic, say. And then we look at this grammar and we see that, unfortunately, it's ambiguous. This is how you fix it. This idea that ambiguity is something that we should just straight up abolish from programming languages is very prevalent. But I'm here today to argue that ambiguity actually does have a place in programming languages. Not everywhere, just in like small select places where it has benefit. So in particular, I'm saying that we shouldn't outright reject ambiguous grammars. We should only reject ambiguous programs. This means that when someone writes an ambiguous program, the compiler should reject it, give a compile time error. And the user should then be asked to rewrite the program such that it is unambiguous, but means the same thing that you originally intended. Now, there's a somewhat subtle point here that's not necessarily obvious, which is, well, is there always an unambiguous way to rewrite things? If not, we have something that we are calling an unresolvable ambiguity. And I'd really like to hammer this in. An unresolvable ambiguity is a really bad thing, because it means that at some point there will be a compile time error that is given to a programmer, and the programmer can't do anything about it. They can't fix it. The only way to fix it is to change the design of the language. So we want to avoid this. But this is POPL, so let's talk definitions. In our work, we see a language as a function. So a function from a program to the set of ASTs that it represents. This isn't a new idea. Compilers do this all the time, but it's unusual in a language theoretic setting. So with this slightly different definition, we define ambiguity to be, well, a program P that can parse as at least two distinct ASTs. If we want to connect this to the standard definition, we can see parse as a mapping from a word to its leftmost derivation, given some particular context-free grammar. And then we get exactly the same thing. Now, this definition that's on screen right now is the definition that this entire talk is about. A program, call it P, is resolvable if for all the ASTs it can parse as, call them T, there exists another program, call it P prime, such that P prime parses unambiguously as T. This is something we want to always be true. So our work today, what we are presenting, has a set of problems that we're trying to solve. The first one is that we need to prove that all ambiguities are resolvable. In our previous work, we had property-based testing for this, which often would find counterexamples if they existed, but not always. In the work today, we have a proof for it. So, be serious. This is going great. So we are introducing a language formalism that is embeddable, which means that you can take any parsing strategy, whatever you prefer, and isolate the parts that need resolvable ambiguity, and then you can use our techniques for that. You can kind of combine them in this way. And for this formalism, we have a mechanized proof that all ambiguities are resolvable, given some fairly mild restrictions that I'll get into later. We also want this formalism to express it. We don't want it to restrict the languages we can, well, express. And there is a slightly different point here, which is that because we support ambiguities, it's also interesting to be able to support different kinds of ambiguity. So it's kind of a different perspective on expressiveness that is also relevant for this work. So to show this, we have taken the canonical OCaml compiler taken out the expression part and rebuilt it using our stuff. And at this point, I should mention that OCaml is a very expression-centric language, which means that things that would be in statements or declarations in other languages, they're just expressions here. So this is a bit more expansive than you might initially think. We also want this to be efficient, because as language implementers, we're kind of spoiled. Parsing is really fast. Typically, it's a tiny fraction of compile times. So for our approach to be useful, it can't be that much slower. It needs to be in the same ballpark. So to check this, we have downloaded all of the packages we could from OCaml. It's package manager, OPAM. And we have benchmarked parsing all of the source files in those packages, which ends up being roughly 1 million files, which is kind of neat. But I promised that I would argue for ambiguity in programming languages, and I haven't gotten to that yet. So let's do that. And the first motivating example that I would like to bring up is that if you write an intuitive grammar for something in your language, it's quite easily ambiguous. This is a slightly simplified production that shows match expressions in OCaml. They look like match expression with, followed by one or more match arms. Each arm has a pattern, an expression, and some symbols in between. This description appears in the OCaml manual. This is slightly simplified from that, but importantly, both what's in the manual and what I'm presenting here is ambiguous. In particular, if we nest these expressions, so in this example right here, we have an outer match that matches against an integer and an inner match that matches against a string. It's somewhat contrived, but small enough to fit on a slide. The first possible interpretation of this is that the last match arm belongs to the inner match. And here I've shown this with added parentheses and adjusted indentation to make it slightly easier to read. Secondly, we could pair the last match arm with the outer match. Both of these are valid according to the intuitive grammar above. But OCaml uses a parsing strategy that requires unambiguous grammars. So it has to pick one of these. It happens to pick the middle one, which, if we look at the original indentation, is probably not what we intended. In fact, if we give this program to OCaml, we're going to get a type error. And it's not entirely obvious if you haven't looked at this before, but what OCaml sees here is that this 2 here, it's a pattern, and it's an int pattern. But because OCaml thinks it belongs to the inner match, which matches on a string, then it's a type error. The way we fix this error is by adding parentheses around the inner match. But this is a bit weird. We're adding parentheses to fix a type error, but adding parentheses does not change the type of anything. With resolvable ambiguity, we can instead see this as an ambiguity error. We can use the intuitive grammar directly, see this as an ambiguity, and ask the programmer to rewrite their program into the middle or the right version, depending on what they intend. Next, we have syntactic composition. And here I'm going to talk about the kind of simplest possible case. So imagine that we have a programming language where you can add custom operators. That means that we can have 2 libraries that add operators. Now, these particular operators, they come from real libraries. They happen to be from Haskell, bonus points if you recognize them. But for the argumentation, the thing that matters is that we have 2 libraries written by 2 authors, and each author has added a parsing table that presumably makes sense for their domain. The issue appears when I, as a programmer, write a program, and I use both of these libraries. The first 2 lines, they're fine. If we understand the operators, we probably understand what this means. And the reason it's fine is because the operators come from one library or the other. They're not mixed. But the third line mixes operators from these libraries. So what does this expression mean? What is the precedence of these operators? Who could even decide what the precedence should be? Because it can't be either of the library authors, because we can't expect every library author to cooperate with every other library author. But the language, well, most languages are written with technology that requires unambiguous grammars. So they have to make a choice here. They have to set some precedence. They have to make an arbitrary choice. With resolvable ambiguity, we can just leave it ambiguous. We get a nice error anyway. In the paper, there are more examples. but in the interest of time, I'm kind of cutting the examples here and moving on to how we are solving this. So on screen right now is a flowchart of parsing with our approach. And I'd like to focus in on a few parts. So first, we've split parsing into two phases. So we have a parser. This would be whatever parsing strategy you would like. And then we have a grouper. And the grouper is the thing that we're introducing. The key point is that the grouper is the only thing that handles ambiguity. All ambiguity is centered into this one component. And the central concept here that is communicated between these two is an operator sequence. So the arrow on the middle of the flowchart. Now, I'm going to zoom in on this a little bit because we have a slightly wider concept of operator than you would normally think. So first, we obviously include, arithmetic and Boolean, whatever, normal operators. Then we also include things that are a little bit larger. So for example, accessing a field in a record. This takes 2 tokens, but it behaves like a postfix operator. So that's fine, still an operator. Next, we have things that contain internal structure of some kind. So the second example here is a function call in a C-like language. Tactically, it behaves like a postfix operator, but inside of the parentheses are arbitrarily complicated expressions. This is fine, still an operator. Next, in the interest of brevity, we're going to call things that don't have operators anyway, nullary operators. And the reason we're doing this is because it's a bit more convenient to say this is a sequence of operators than this is a sequence of operators and things without left or right recursion. And finally, the tricky part that is a bit unusual is that, well, we said that all ambiguity lives in the grouper. But the match example I showed earlier, it doesn't really look like it has to do with operators. So what we do is that when we have something that isn't quite operators, but still needs to be expressed in an ambiguous way, is that we split it into operators. So the kind of simplest example is if we have an if-then-else with an optional else. If we nest these, we get something very similar to the match expression before. So we say that if-then is a prefix operator, and else is an infix operator. And then we kind of work with those as regular operators and merge them towards the end of parsing. So let's briefly go through the data that kind of goes through this flowchart. And this is going to be a bit of a whirlwind tour. But rest assured, all of these figures are explained in rather more detail in the paper. So we start with a program fed to the parser. The parser is then responsible for finding operator sequences in this program. And they might look like this. Notably, this will happen multiple times in a program. So this operator sequence covers the entire program, but there are also some smaller ones. Say the condition inside the if-then. That's the small operator sequence of length 3. Next, the grouper takes the sequence and arranges it into a tree, according to an internal specification that we're going to talk about slightly later. Importantly, though, the if-then-else is still split here. So we still have splittable productions in split form. Next, we return it back to the parser, which then produces an AST. Most importantly, it merges if-then-else. But in practice, it's also going to do some more things, more details in the paper. So all ambiguity lives in the grouper. And we have a proof that talks about ambiguity. That means that all our formalism lives inside of this grouper. So intuitively speaking, we see grouping as a series of rewrites. So we start with a sequence of operators, and this is the same one I showed on the previous slide, just a bit briefer. So if instead of if-then, and fc instead of call for function call. Then we focus in on some part of the sequence that's kind of done. It has already been grouped as much as it's going to be. In this particular case, the rightmost variable. Then we check, can this thing be grouped to the left or to the right? In this case, function call has higher precedence than else, so we group it to the right. But now the function call is done. It has all the children it needs. So now we can see where it can be grouped. In this case, to the left. It becomes the right child of the else. And then we kind of keep doing this until at the very end we reach some completely grouped expression. Now, like many rewrite semantics, it's not always obvious which rule you could do, and sometimes you have different choices that kind of produce different results in the end. And this is intentional here, because if we can do multiple of these rewrite sequences that end up in different fully grouped results, that means we have an ambiguity. This is how we define ambiguity at this level. The grouping specification that we work according to is split in two parts. The first one you can intuitively think of as binding strength. And this is things like if you have multiplication on the left and addition on the right, the thing in the middle must go to the left. And it's worth noting that this is not symmetric. So we can say things like addition on the left, addition on the right, the thing in the middle must go to the left. And that means the addition is left associative. Then we have something that we're calling shallow restrictions. And with this we can say things like the left child of else must be precisely an if. It can't be a number, it can't be addition, it can't be a grouped expression, so it can't be parentheses. It must be exactly an if. The if can have other children, but the root node of the left child of an else must be an if. And this lets us kind of keep the mapping between if and else through the grouper until we merge later on. The actual formalism now is here on the right-hand side of the slide. And it fits on the slide, which is neat. So it's actually fairly small. But given that this is a relatively short talk, and I'm trying not to bore you, I'm not going to go into detail about all of these things. But I would like to focus in on the middle left, which is the grouping specification. So bind at the top, that's the binding strength. And then a left, a right, and a root, those are the shallow restrictions. And these are expressed as sets of what's allowed in this position. The rules have a significant amount of symmetry. So these four rules are split based on, is the thing we're looking at moved to the left or to the right? And is it found at the edge of the sequence or somewhere in the middle? The bottom two rules kind of do everything else that's left. So we remove parentheses, grouping parentheses, and then LR steps takes a sequence of these steps. So it kind of ties everything together. With all of this said, the property that we are actually proving is this one. And this is the thing that I showed you at the beginning, but with an extra for all P at the very beginning. So we want the thing to hold for all programs. And as a completeness thing, this is the definition of parse that we're using in this paper. So we're connecting it to the formalism on the previous page. This up here on the right is the restriction we're using. And this looks a bit hairy if you're not used to the formalism. But the intuition isn't that difficult. So looking at that, the first 2 points, if we start with those, they concern if we have a splittable production. That means that at some point we're going to have kind of a sequence of operators that should be together. They should be from the same production. So for if, then, and else, that's just two productions. But to put these in the tree, one of them has to be a parent of the other. And we have to make a choice of which one should be the parent. It turns out to be convenient for our proofs to make else the parent, so we choose the right one. And that's what point 1 and 2 in the restriction say. The last 2 points, they can be said slightly simpler as, for each operator, it either must be first in a split production, or it must not be first in a split production. And slightly more intuitively, this means that at the beginning of a split production, there must be something that kind of signifies that it starts now. And this is already true in most programming languages. If, for example, is a very clear signifier that this starts for an if. We benchmarked these things, and there's a bunch of stuff I could talk about here, but the kind of key takeaway is mostly visible in the right plot, which is the absolute slowdown. So 99% of files still parse within, I think it's 12 milliseconds, and the absolute worst slowdown from the original OCaml to ours is, I think, roughly 0.42 seconds to 0.72, something like that. So parsing is still quite fast. It's still mostly hard to notice in interactive use. So we're still practical efficiency-wise. So, time to conclude. Commonly, we have no ambiguity in programming languages. But we're arguing that it has a place as long as it's resolvable, it is at, it's not everywhere. It's just in places where it's useful. The approach that we are introducing here is embeddable, so you can combine it with whatever you like. It's expressive. We've expressed OCaml's expression language, which has a bunch in it. It's still rather efficient. Not as fast, but the difference is minor. And finally, and certainly not least, we have proven that all languages defined in this form are statically resolvable. Thanks for listening.
Yes, there is a question.
Thank you. Tom from Utrecht in the Netherlands. So thank you for the amazing talk. One thing I was wondering, you said that you basically defined ambiguity at this operator level as there being different sequences of real applications that arrive at different parsed results. So how do you distinguish actually different choices from just different applications of the rules to different parts of the expressions that eventually end up doing the same thing? How do you avoid this combinatorial explosion?
So formally speaking, that can happen. The actual algorithm that we've implemented to do this in practice does not apply these steps in this way. It applies them in a fixed known order, and instead of building all of the trees, it builds a shared packed parse forest to be efficient. So we are kind of sidestepping the issue. Formally speaking, you have this combinatorial explosion, for sure. But implementation-wise, we're avoiding it.
Isabel has an interesting approach to handling ambiguous parses where they take all the parses and type check them. And if only one of them type checks, then that's the resolution. Could you incorporate that sort of thing into your notion of resolvable ambiguity or controlled ambiguity?
Theoretically speaking, yes. So you could implement a pass that takes the shared packed parse forest and you kind of filter it based on type checking information. But it's not obvious that you want to do it. So one thing is that you still need to construct all of these, this parse forest along the way, which is a cost, performance-wise. The second point is that means that when I read this code, I need to essentially have a type checker running in my head to understand the code. And to some extent, that's true for more parts of the code, but it's not as obvious that it's correct here. Obviously, Isabel does it, and it works there. But then again, Isabel is a relatively advanced language, and people that use it tend to, have a lot of experience with type systems and whatnot. So it is doable, but I'm not entirely sure that you want to.
Singhyun Nam from Seoul National University. So the first impression I got from your talk is that it might be really helpful to, generate a more helpful debugging or error messages for programmers. But, so I wondered if if your approach is applicable to almost every languages, for example, like C++, or does it depend on some special characteristics of the programming languages or stuff like that?
So the core assumption that is needed for the way we're implementing it right now is that you can extract this operator sequence, and that it's useful to do that. So essentially that means that without thinking too hard, you should be able to identify that this is where an expression starts and this is where it ends. And these are the components of the expression. As long as you can do that, you could integrate this work into it. So it should still be doable for C and C++. And I'm not entirely sure that it would avoid the issue that C++ is not context-free. I think that would still have to be solved in the similar hacky way, but I think you could do it still.
Thank you.
Hi, Michael Smith from UC San Diego. Can I steal this? Because this is great, and I have a bunch of places I want to apply it. How reusable is the machinery you developed outside of OCaml?
So implementation-wise, we've written this inside. So in our research group, we have a language framework that we're working on, miking. You can talk to David over there, who has more information. But we've implemented in that as a library, and then from there, we have kind of compiled it to OCaml as a backend. So we have an OCaml module that you can interface with. Beyond that, there's nothing in the implementation that is all that weird. So if you have a functional language, it shouldn't be that difficult to port it. But it is implemented as library, so it's relatively reusable.
Fantastic, thanks.
Okay, so thanks again the speaker and all the three speakers